be presenting my PhD research proposal titled Towards Agile Vision Language Models, Efficient Adaptation to Dynamic Tasks and Users. The central theme of my work is how can we enable VLMs to efficiently adapt to changing tasks and evolving user needs without relying on costly retraining or large external datasets. To start, let me briefly introduce vision language models or VLMs. VLMs are models that have been trained jointly on internet scale data related to vision and language tasks. Once trained, these models have shown to achieve very strong zero-shot generalization across tasks like captioning and PQA. But the important point here is that once trained, these models are static, and that's the limitation I'll focus on next. To see why VLMs being static is a challenge, let's look at an example. If I ask a VLM to describe this image, the VLM will correctly generate a caption saying, this image consists of a Labrador sitting on grass. However, if I ask the same VLM showing an image of my dog and ask it, can you see my dog? Or suppose say, can you identify my neighbor's dog in the image? The VLM will fail to do so and generate something like, sorry, I cannot help you with that. The issue is that while VLMs are powerful, they are static once trained, whereas real world needs are dynamic. That is, the tasks or even the visual concepts are always evolving. So the key challenge is how can we adapt these models efficiently without retraining or storing sensitive user data? This brings us to the two key adaptation challenges for VLMs that I have focused on in my work. The first is continual learning in VQA. VLMs need to handle questions across a variety of domains, from answering questions related to everyday objects and activities to answering questions from medical or even agriculture domain. Now, continual learning lets a system gradually acquire knowledge from different domains. But in practice, when new tasks are learned sequentially, the model suffers from something called catastrophic forgetting. Current fixes often rely on replaying stored past data. However, this raises storage as well as privacy concerns. The second challenge that I have focused on is personalization. Users may want VLMs to recognize their own concepts, such as my dog, my mug, etc. But current solutions usually require the models, the existing VLM models to be fine-tuned or retrained per user or per user concept, which is highly inefficient and very computationally very expensive. My research addresses these two challenges, continual learning and personalization as the foundation for building truly adaptive VLMs. VQA is a strong benchmark for multimodal reasoning, but today's models still struggle with structured concepts like attributes, states, and spatial relations among objects present in the image. So these models need to be continually updated to stay reliable. In practice, VQA tasks, they don't arrive all at once. New questions, new question types, concepts, and compositions appear over time. A good model should learn them incrementally without forgetting what is already known. Most continual learning methods rely on storing past data, which is also known as rehearsal. Now, storing past data is fine, but this creates privacy and memory issues. So the key question is, Can we enable continual learning without storing past data? And this is something that I've worked on as the first part of worked on as the first project in my PhD. Traditionally, continual learning, these methods rely on rehearsals, storing past data, and mixing it with current data during fine-tuning. But this is not always feasible because, as I mentioned, privacy or storage costs. Now, let me show you how our proposed method, GAB or GAB, solves this with pseudo rehearsal, eliminating the need for stored past data. In GAB, instead of storing past data, what we do is we leverage the generational capacity of our VLMs. Given the images for our current task, we prompt the model to generate questions as well as answer pairs as if they were from the earlier task. So what we do is for each task, we have a question generation head, which learns the question answer distribution for each of the tasks that the model has seen before. When a new task arrives, we use the trained question answer heads to generate question answer paired for the current task images. In this way, the model rehearses without needing to keep whole data, right? Because here we are just storing a single layer of weights, and we do not require to store the past task images. But how does our method generate pseudo rehearsal data? For each task, as I mentioned, we train a lightweight task specific head to capture the question answer style of that task. When a new task arrives, these heads generate pseudo QA pairs from the past task, but on the current task images. This way, the model rehearses on old tasks without storing their data. Once we have generated rehearsal data, we mix it with current task data, uh, shown here. The model is then trained jointly on both with task-specific uh, classification loss, LCL, and question answering loss, LQA. The joint training lets GAB learn new tasks while maintaining performance on old ones, effectively reducing forgetting without ever needing past task data. Simply generating pseudo rehearsal data isn't enough. The generated data often skewed towards certain question types which are more frequent for a certain task. To fix this, we compute the true distribution of question types for each task and rebalance the generated data to match the true distribution. This prevents bias and ensures diversity in the rehearsal set. Quantitatively, GAP performs on par with the rehearsal-based methods in terms of accuracy, but crucially without storing any past data. Compared to data-free baselines, GAP achieves lower forgetting, down to 1.4 versus 10 to 16 that we see for methods like MAS or LTP. This shows that GAP's effectiveness in retaining knowledge while adapting to new tasks. To summarize, GAP shows data-free continual learning in PP way is possible. It mitigates catastrophic forgetting without storing past data by generating pseudo-rehearsal QAs and balancing them across question types. Now let's talk about the second problem in adapting VLMs, which is actually personalization. Personalization allows a model not just to recognize objects in general, but to recognize and reason about concepts specific to a user. For example, my dog, my mug, or even a person like cow, which I've shown in this figure. With just few reference photos, a model can be personalized and then asked to recognize the concept in new images and answer visual questions involving them, or even handle text-only queries. Recent works on personalization mostly fall into two categories: parameter efficient fine-tuning, such as adapters or LoRa's, and expensive large-scale pre-training of synthetic datasets. While effective, both approaches come with significant downsides. Either they need retraining per user or cost of generating synthetic data can be massive. The problem that we are interested in solving is, can we exploit the internal knowledge of a pre-trained VLM to perform personalization without training? To address personalization, we introduce R2P, a training-free method that uses textual fingerprints to identify concepts. Unlike prior methods that require fine-tuning or test and training, R2P combines retrieval and reasoning to achieve personalization. This allows the model to recognize concepts like my CVPR t-shirt based on what makes it unique, such as color, logo, or shape without retraining. This approach achieves state-of-the-art performance on personalization benchmarks while remaining efficient and data-free. To evaluate this properly, we also need a more realistic data set, which brings me to our proposed data set in the paper, which we call as per VA. Existing personalization data sets are quite limited. They usually contain only a small number of concepts captured in clean and ideal conditions. To test the model under more realistic settings, we built per VA. It includes around 329 concepts across 21 everyday categories, such as clothing, headphones, trolley bags, etc. Importantly, the objects in per VA appear under varied viewpoints, poses, illumination, which makes recognition far more challenging and realistic. This ensures that the personalization that we do is not just in controlled lab settings, but under a condition closer to what actually happens in real life. Now, R2P, or the method that we propose in our work, it works in two phases. First, we build a personal database of the user's concepts, enriched with uh, distinctive attributes in the form of text. And in phase two, we perform inference, which retrieve and reason. Given a test image, we retrieved top K images from the database based on visual similarity as well as the description for those reference images. Then we asked the model to do a chain of thought, attribute attribute focused chain of thought based on the query image and the retrieved descriptions. Once the concept is recognized, the model can generate personalized captions or even answer personalized queries. Let's look at some qualitative examples to see how R2P actually behaves. Here's the example of a cloth called FAC, and the user might ask, caption the image for me. Uh, Without personalization, the model might confuse it with any other fabrics in the database, but R2P uses fingerprint attributes. It notices those fine-grained nuances like light pink, smooth texture to correctly identify it as FSC. Similarly, in the plush toy example, there are multiple similar concepts, and R2P reasons over the distinctive attributes like the sleeping posture and is able to identify it as the toy Shiba Sleep, even though the other retrieve concepts are quite similar. But by focusing on certain distinctive details, it can correctly identify the concept name. Now, quantitatively also, R2P outperforms prior methods across multiple personalization benchmarks. On MyVLM and ULAVA, R2P matches or exceeds the strongest baselines. And importantly, on newer, our own proposed Purview data set, which is much more challenging, R2PA achieves over 90% accuracy, a clear margin over existing methods. So qualitatively, we saw that it can disambiguate similar concepts, and qualitatively, we see that generalizes across data sets, establishing R2B as a state of the art for training-free personalization. To summarize, with R2B, we show training-free personalization is feasible. It achieves strong results across benchmark, even on challenging per VA dataset. Looking ahead, uh, I'd like to work on making this approach much more efficient and robust. In real world, cluttered, dimly lit, or even in occluded settings. So till now, what we saw is in the personalization space is that the method we proposed is a training free, but since we are relying on a pre-trained vision language model, it we often face the problem of hallucination in its reasoning process. To address this, our next step would be to fine-tune the VLM with reinforcement learning approaches like GRPO, which have been recently shown to show strong generalization performance, but with limited supervision. This will allow us to make personalization even more robust and reliable. In the future works, I would like to explore how we can do multi-concept personalization. As in the image you can see, given two concepts, can the model reliably answer questions like, can you see Tom's bottle beside my bottle? RTP can handle only one concept at a time, but the next step would be to uh, show that the model that we propose or the method we propose can handle multiple user concepts at a time. Another area that we'd like to explore is, can we reliably personalize user concepts in different environmental settings, such as when the objects are in a dimly lit room, or if the object is occluded, or if the object is present among various other objects in a cluttered scenario. And the third would be to show that we can continuously adapt our model to from identifying objects in a clean, well-lit environment to identifying them in dimly lit. And then what happens if the environmental scenario changes to wooded scenario, cluttered scenario, and to multi-concept scenarios. So the model should continually adapt to different environmental scenarios without forgetting what it had learned in the past. Finally, this is my research plan. Till now, uh, I have been able to, uh, uh, I mean, in my in a second paper, we have been able to publish. And right now, I'm doing literature survey for our third work, which is on multi-concept personalization as well as robust personalization. We plan to submit this work during the months of October, November in CVPR. Then next year, I plan to do an internship. My co-advisor is in CVC Barcelona, and I intend to spend like 3 months there. During that time, I'll be working on how we can continually adapt our personalization to different environmental scenarios. And finally, the after submitting this work, I'll be focusing on writing and submitting my thesis from between May and October 2026 and submitting it. So to conclude this work, our work tackles fundamental challenge of making visual language models adaptive. With R2P, we show that training-free personalization is possible, and with CAP, the training-free data-free continual learning can mitigate forgetting. Together, this contribution point towards a future robust continual multi-concept personalization where VLMs can adapt seamlessly to evolving users and environments. Now, be addressing the main concerns from the previous commissions and how we have uh, adapted our report as well as presentation based on the feedback. So the previous commission highlighted several important issues. First, that both my report and presentation focused mainly on back the paper that we submitted without being framed as a full research proposal. Even the future work section was brief and not very well connected. Second, my personalization work jumped across topics like continual learning, personalization, and federated learning without unifying narrative. And finally, what was missing was a higher level view, a clear articulation of the overarching research goal, and how my contributions fit into consistent plan. These are the points that I've addressed in my revised report and today's presentation. So let me first iterate. Uh, sorry, the research goal that we are trying to solve in this PhD study. The research goal that we're trying to solve is how can we develop or how can we train models, VLMs, which can adapt or continue to learn and personalize without relying on external data. This breaks down into two sub-questions. First, continual learning task addressed in my gap work, which enables VLMs to learn new tasks without forgetting. The second question that we try to answer is how can VLMs efficiently adapt to user-specific concepts? This was addressed in our R2P work, which allows efficient training-free adaptation to user-specific concepts. And third, in our future works, we would like to unify or try to unify both these directions into robust continual personalizations where models can handle multiple evolving user concepts under real-world conditions. And this will be as I mentioned, will be the focus of my future work. Uh, Now, let me just go back to the concern one. The first concern was that my previous report was essentially my background paper with few added paragraphs. In this revisions, I have reframed the work as a proper PhD proposal. Each contribution is now explicitly tied to overarching research goal, and the future work is developed in a concrete roadmap rather than an add-on. The second concern was that my presentation lacked coherent storyline, jumping across multiple big topics. In this version, I focused on two complementary sub-questions, continual learning and personalization. These are now clearly situated as a step towards an overarching goal. Future work is framed as their unification rather than a disconnected set of ideas. To summarize, I have addressed the main concern raised by the previous committee. The report and the presentations are now structured as a proposal rather than just a paper. The storyline is unified around two core challenges, and the future work is framed as a coherent research roadmap. I believe that these changes address the earlier concern and demonstrate that proposal has a higher level view of what I'm trying to achieve. That's all from my end. Thank you, and if you have any questions, please feel free.